Students, we will continue this topic, basic theorems of Boolean algebra. In the last video class, we have completed up to theorem number 13. Today we will see these three theorems. These three are identified as distributive laws. Okay, so chapter is Boolean algebra, second chapter, class number 7. So here I am going by two methods as usual. Method 1, proof by perfect induction. Method 2, using truth table. And last I will see this circuit construction for the given theorem. So the circuit construction involves the construction for the LHS expression and for the RHS expression. Okay. So I will take the first one, the 14th theorem. So here it's of x of y plus z equals to x into y plus x into z. Okay. So let me go for first proof by perfect induction method. There, as usual, take any one variable out of x, y and z. Take any one. Okay. So you substitute 0 for that variable one time, and in the second time substitute value 1 for that variable. So both the times, of course, we are going to get LHS equals to RHS. Then we will see finally that because of the LHS equals to RHS, theorem is proved. Okay. So prove by perfect induction method. Let x equals to 0. I have taken the variable x, okay, out of x, y, z. So substitute x value as 0 here in this given statement, the 14th theorem. Okay, so 0 in the bracket y plus z equals to 0 and operation y, or operation 0 and operation z. Okay, so we'll use the properties of 0. So the starting two theorems, the properties of 0, and in the properties of 0 we are having two theorems. When 0 is ANDed with a variable, and when 0 is ORed with a variable. So here in this case 0 is ANDed with the variable. So here 0 is ANDed with this expression y plus z. Here 0 ANDed with y and 0 ANDed with z. So when 0 is ANDed with an expression of the variable, answer is 0. The properties of 0. So we are making use of that theorem. So 0 equals to 0 into y. Okay, again the 0 into x equals to 0. So here 0 into y equals to 0 plus 0 into z equals to 0. Then LHS is very clear, it is 0. RHS, both are 0, it's an OR operation. Okay, so it is 0. So LHS equals to RHS. Let it be 1. And similarly, we will now substitute value 1 in the given theorem. Okay, so 1 in the bracket y plus z equals to 1 into y plus 1 into z. So now we will use the properties of 1. So in the properties of 1 we are having two theorems. When the value 1 is ORed with a variable and value 1 is ANDed with a variable. So here value 1 is ANDed with the expression, and again value 1 is ANDed with this expression, of course, one single variable. 1 ANDed with a variable, 1 ANDed with a variable. Okay, so this y plus z we can see it as just something like single variable, because finally we are going to get one value when we go for y plus z. Okay, so in that way 1 into x equals to 1, we will use that one. So property of 1. So now 1 plus this one is going to be y plus z on the LHS equals to 1 into y is y plus 1 into z is z. So LHS is equals to RHS. That will be 2. So conclusion. So what you can write from questions 1 and 2. Okay. So from 1 and 2, the theorem is proved. This is about the proof by perfect induction method. Okay, so now come to the truth table method. So we can use the truth table, and we are having of course three different variables here in this theorem. So when there are three different variables, we are going to get 8 possible cases of, or you can say combinations of zeros and ones, starting with the triple zero. Okay, the binary equivalent of decimal 0. Then it is going to be 001, 010, 011. Next 100, 101, 110, 11 and 1. So triple one is a binary equivalent of decimal value 7. Okay. So first we have to write the combinations for the given three variables x, y, z. Okay, the binary combinations. So once it is ready, now we'll go for, let's say, first LHS part. So here within the bracket we have to give first difference y plus z. OR operation is there, so we'll go for the y plus z. So these two columns we have to refer. It's an OR operation. So when both are 0, then only it is 0. If not, it is going to be 1. Okay. So now for remaining boxes, I fill with binary value 1. Next, outside the variable x is ANDed. So we'll go for that one. X of y plus z. So y plus z column, then the column x, and it's an AND operation. If nothing is there means it's a dot and it is AND operation. So AND operation is going to be 1 when both are 1. Okay. So just see for 1. So x is here, y plus z is here. If both are 1, it is 1. Okay. So remaining cases, this expression gives us the value 0. So now LHS part is completed. So we got 5 zeros, then 3 ones continuously. So same value we have to get for the RHS part, x, y plus x, z. So if that is the case, then we can say by method 2 using truth table also the theorem is proved. Okay, then we'll go first this x into y plus, because AND operation we have to give first preference, then x into z will go, then we'll go for ORing operation. So x into y, then we'll consider x into z, lastly we'll go for OR operation, that is plus operation, x into z. Okay, so x into y. So AND operation between x and y, if both are 1, then only it is 1. So both are 1. In the last two cases it is both are 1. So here we are going to get 1. So remaining cases it is 0. So similarly x into z, the column x and z. Whenever you see both as 1, you take answer as 1. So remaining cases zeros. Now lastly, between these two columns, x into y, x into z, okay, go for the OR operation. So it is 0 when both are 0. So both are 0, 0. Both are 0, again it is 0. Okay, continuously we are getting zeros here. So in these three rows, we don't have both as 0. So answers for these three are 1. So now we will observe this column with this x into y plus x into z. So here is this x of y plus z. So continuously 5 zeros, then continuously 3 ones. Here also we are getting, so we got continuously 5 zeros, then 3 ones continuously. So again, so whichever method you write the conclusion. Okay, don't skip this part. So in the truth table, okay, so the columns, which are those columns? X of y plus z, this column and that one, and xy plus xz are same Hence the theorem is proved. Okay. So now we'll go for the circuit. Okay. So how the circuit is going to be for this theorem, separately for LHS and for RHS. So it's three different variables here. Okay, then I will go for x, y and z. So within the bracket, first we have to consider within bracket between y and z, it is OR operation. So OR gate. So its result here it is what? Y plus z. Now it is going to be an input for the next level gate. So now this answer is ANDed with the variable x. So ANDed means capital D AND gate. So this side it is as AND gate. So x into this y plus z. So this much of circuit connection is equivalent to the other circuit. So this circuit is of for this purpose, x into y plus x into z. So for RHS. So again, as usual, three variables we are having here: x, y, z. Okay, x into y AND gate. So this output is x into y. Then we need x into z. So what you can do, you go for some adjustments here. Okay, you can take a line like this from the variable x. Okay, so this line is from the variable x. Then this is the line z. So x and z lines we are having, input signals we are having. Then go for one more AND gate. So this result is of x, z. So now both the results or both the signals are then odd, means taken into the OR operation. So these two signals now will take with OR gate. Now finally, what is this one? One side is x into y, then the other line is actually result of x into z, and it's an OR gate, so plus symbol. Okay. So this circuit circuit construction is equals to this one. So both the circuits gives you this result. Okay. So for the these combinations of input values for x, y and z. So easily we can say that this is better than that one, because there we need 3 gates, here we need only 2 gates. Moreover, both the circuit connections gives us this same result, because we are seeing this column and this column both are same, or else by method one you can say because of this and this. Okay, so we can say these two are same. Okay, so now we'll go for the other theorem, 15th theorem. So again we are having 3 variables here, x, y and z. Okay, so first I will consider the proof by perfect induction method. So take any one variable x, y or z. Take 0 one time and 1 another time. Okay, let me say x. So I have taken x. So x is 0. Substitute that 0 here in the 15th theorem. 0 plus y is z. And on the RHS part, 0 plus y and 0 plus z. Okay. So left hand side, the property of 0 we use whenever 0 is odd with an expression of the variable or the expression itself is an answer. So 0 is odd with this yz. So 0 plus x is x only, the properties of 0. So now 0 plus yz is yz only. Okay. So this side 0 plus y is y, plus 0 plus z is z. Okay. Here we are again. Okay. So y into z. So LHS equals to RHS and it is 1. So now we will substitute value 1 in LHS and in the RHS. So of course we are going to use the property of 1. So in particular case where 1 is odd with the variable. So when 1 is odd with the variable, answer is going to be 1 only. Okay. So here 1 plus yz equals to 1 plus y 1 plus z. So 1 plus yz is 1. This side 1 plus y is 1 into 1 plus z is 1. Next line 1 equals to 1 into 1. 1 ANDed with 1. So both are 1 and operation is answer 1. Okay, so again LHS equals to RHS even when you consider x as 1. So from 1 and 2 theorem is proved. So by perfect induction method. So now take up the truth table now. So this x, y, z column is same. From here onwards we have to go for some changes. So now the table is ready. So only x, y, z I am retaining in the previous truth table. Now we'll go with the columns and the values for those columns. Okay. So we have this one on LHS for x plus yz. So yz will consider first because of the AND operation. So yz. Then we will consider x plus yz. So this is about the LHS part. So RHS, okay, x plus y one time, then x plus z another time because they are in the bracket. So bracket we have to do first preference. Then we go for the AND operation. Okay. So first we need x plus y, then the x plus z, then finally x plus y, x plus z. Okay, headings are ready now. Now we will identify the values. Okay, so yz. So into operation, both are okay. So both are 1, then it is 1. So remaining cases zeros. Okay. So then x plus yz. Yz column is ready. So x is here. It's an OR operation. Okay, OR operation. When both are 0, then it is 0. Otherwise it is 1. So what about this one? Yz. Yz. So it is 0. So x plus yz. So in all the remaining cases it is going to be 1. So this is completed, this x plus yz. So same result we have to get for this side also. Okay, because theorem is given already, so it has to be same. Say x plus y first, say both are 0, then it is 0. Both are 0, x and y. In the remaining cases it is going to be 1. X plus z, between these two columns, both are 0, then only it is 0. Only one case. Remaining all the cases we are getting 1. Now we are going for the AND operation between these two columns, x plus y and x plus z. AND operation means it is 1 when both are 1. Okay. So here no, from here onwards we are getting both as 1. So for this answer is 1. Starting 2 it is 0. Okay. So now check it. This column x plus yz, 3 zeros, 5 ones. We are having 2 zeros, 6 ones. So somewhere I did mistake here. So where it is? X plus yz. Yz is 0, so x is 0, okay, that is 0. X plus y. X plus here I have to get this one as 0. So see here x plus z is there. So x plus z, in this case both are 0, so I have to write 0 here. Okay, so now x plus y into x plus z, x plus y into x plus z, both are 1, then only it is 1, it is not it. So here 0, here 0, here both are not 1, so it has to be 0. So in the remaining cases it is 1. So finally we got, so same columns, x plus y z column, 3 zeros, remaining ones. For this also 3 zeros and remaining all are 1s. So finally conclusion, in the truth table, okay, so in the truth table the columns, okay, so which are those columns? X plus y z, x plus y z and x plus y, x plus z. Are same, hence the theorem. Okay, so we have proved the 15th also by both the methods. So let us consider the circuit. Okay, so gate representation. So 3 variables we need. In the latest case, y into z will consider first. Y into z in the case it is AND operation, it is yz. Or with x, okay, we have to go for OR operation. An OR gate. Okay, so this one now, one input is x, OR gate is plus, other line is yz. So this is completed for this x plus yz is going to be equivalent to the other part. Okay, x plus y and x plus z. So x and y OR gate. So then it will become x plus y. So now the x plus z. So x line will take like this. Okay, this is the line z. Again you need OR gate. So this OR gate result is what? One line is x, the other one is z. So x plus z. Finally we need AND gate. So one line it is x plus y dot for the AND gate. So x plus z on the other side. So whether this or this, whichever the circuit we are having or constructed, both will give you the same results. It was 0 and 5 1s. Of course, which is the better one? This is the better. We need only 2 gates. Here we need overall 3 gates, 2 OR gates, then 1 AND gate. So here 1 AND gate and 1 OR gate is enough. Okay. The 16th one, it is simple compared to the previous 2, because in the 16th we are having only 2 different variables. Okay, that's why I changed that to table. Now we are going to have only 4 rows. So let me take up this 16th one, the last theorem in this distributive laws. So x plus x complement y is going to be equal with x plus y. So it is same as that x plus y. So prove by perfect induction. Let me say x equals to 0, substitute 0, 0 plus 0 complement y. So in place of x, okay, 0 is a complement. So 0 bar. So 0 complement and then dot operator and y. On right hand side it is 0 plus y. So now 0 plus 0 complement is 1. Okay. So it is now 1 into y. So 0 bar, basic postulates, complement rule. Complement of 0 is 1, complement of 1 is 0. On this side it is 0 plus y. So properties of 0, that theorem 0 plus x is x. So 0 plus y is y. So here 0 plus property of 1. So when 1 is added with a variable, answer is the variable. Okay. So 1 into y is y. This side it is y as it is. So 0 plus y is y. Properties of 0. The right hand side again it is y. So finally it is LHS equals to RHS. Okay. So it is y and y. Now we will substitute the other value. So x equals to 1. That theorem 1 plus 1 complement then into y equals to 1 plus y. So complement of 1 is 0. So this is going to be 0. This one will keep that one as it is. So 1 plus 0 into y. 1 plus y is y only, property of 1. So 1 when it is odd with the variable, answer is 1. Okay. So 1 plus 0, property of 0. When 0 is added with a variable, answer is 0. Okay. So 0 into y is 0 equals to 1. So on the LHS we are having 0 plus 1, that is OR operation. Okay. Basic postulate of OR. So when both are 0, then only it is 0. That's why it is now 1 here. Right hand side already we are having 1. So LHS equals to RHS. So in both the cases we are getting LHS and RHS as same. So final conclusion, from the equations 1 and 2 the theorem is true. So now we will go for the truth table. Now it is simple, we are having only 4 rows. Okay, so 2 different variables here are x and y. So write the combinations 0 0 0 1 1 0 and 1 1. And here one of the variable is complemented. The variable x is complemented. So let's go for a column as x bar. So whatever the value here you are having in this column, you write its opposite value. So 1 for 0 and 0 for 1. So this is now x bar column. So now next we will go for x bar into y. So x bar we have considered complement. So not operation we have to consider first. So I have taken x bar. Okay. Then I can go for the AND operation. Lastly, I can give preference for the OR operation. So we have to follow the precedence rules. Not first, then AND, then OR. Overall on these 3 brackets. Okay. So we don't have any brackets there. Now we'll go for x bar into y. So x bar column is here into y. So here. So x bar y. So AND operation is there. So when both are 1, then only it is 1. Okay, so x bar and y. When both are 1, it is 1. So in the remaining boxes, I go with the zeros. So next is, still we need to go for one more operation in the LHS side, OR operation. Okay, x plus x bar y. So x bar y column is here. We will go for OR operation with the variable x. So these two are OR operation. So OR operation in the sense, answer is 0 when both are 0. So both are 0, here it is 0, in here it is 1, here 1, again here it is going to be the 1. So now this LHS part is over. So you got 0, 1, 1, and again we have to get the same 0, 1, 1 for x plus y. So that side it is very simple, just x plus y here, the OR operation between the two variables. Okay, so x and y columns, and we have to go for the OR operation. So both are 0, then only it is 0. So here both are 0, here it is going to be 0. In the remaining cases it is 1. So from the above table, the columns, this one, x plus x bar y and this x plus y and x plus y are same. Hence this theorem is proved. Okay, and of course it is by using truth table. So lastly we will consider the gate representation. Okay, so in the examination, whichever method you have taken, method 1 or method 2, okay, of course as I said, usually we won't see any condition whenever we see a question for proving any of the theorem. So choice will be on the student side almost. So we can solve by using this one or this one. Lastly, better you go for the gate representation, particularly when you are having more marks. Okay, so when you are having more marks, better finally you go for the gate representation. Now, gate representation for this one, only two variables, the line x and another line or say signal y. So x complement is there, so we have to go for the NOT gate for the variable x, or for this signal, whatever the value you are getting here, we have to reverse the one. So arrow mark and bubble symbol. So this side is going to be now x bar. So x bar, then it has to be ANDed with the variable y. So ANDed in the sense the other line, when it is taken, then we have to go for the AND gate. So x bar y, or with the variable x. Okay, so here these two lines are odd means OR gate, OR operation. So one line is what? X bar y, OR gate, so plus symbol. Then this side it has to be x. So this line will take it to meet this line. Okay, so take this line before this NOT gate. Okay, because we need x here. Okay, so from here you take it as another input signal for this OR gate. So this circuit construction having three gates, NOT, AND and OR, it is giving the same value as of for the x plus y. Okay, x plus x bar y is giving the same values, whatever the values we are getting for this operation x plus y. So for this one OR gate x plus y. Okay, so both these circuits are identical, or you can say same. So all the distributed laws are completed. Still we are having two theorems, 17 and 18. Those two are called as absorption laws. So I will take up those two theorems in the next class.